We're very happy to have Wolfgang Altmannshofer up from Santa Cruz, and he's going to tell us about hints for new physics and rare B decays.
Right. Thanks a lot. Thanks for the invitation. It's a pleasure to be here. And I will talk about hints for new physics in rare B decays. So since a few years, there have been experimental results on the rare B meson decays, which show discrepancies with standard model expectations. And I will tell you a bit about these discrepancies. I will discuss how significant they are, which of these discrepancies you should believe, which ones maybe not, and to which extent they could be interpreted as hints for new physics, and which type of new physics this could be that is showing up in these rare B decays. So part of the talk will be related to these measurements here. These are experimental results from the LACP collaboration, measurements of observers that are called RK and RK star. I will define them later in the talk. For the moment, it's just important that these are observers that test lepton flavor universality in rare B decays. And the standard model predictions for these observers are 1 to a very high precision. And then on these plots, you see the measurements of RK and RK star in bins of Q squared, where Q squared is a kinematic observable related to the B meson decays that these observers are measured in. And the standard model predictions are 1 with high precision, and the measurements here are measurements from Babar and Bell, and also here Babar and Bell measurements. And then the LHCb measurements from a few years ago, which are the by far most precise measurement of these observers that we have so far, and they deviate from the standard model prediction by around 2.5 sigma in 1 bin in RK and in 2 bins in RK star. So that by itself might be already some pretty significant indication that there's something going on. What I will discuss in this talk is that before these measurements came out, there actually were a series of other measurements that were discrepant in rare B meson decays. And these results actually are very nicely compatible with these older measurements, with these older discrepancies that have been around since a few years. And I will try to sort of build a picture that this could be a consistent way how new physics might be showing up in the rare B decays. Also very exciting, these RK measurements is supposed to be updated in a few weeks at Morion 2019. So this measurement of RK, we will have soon an update of that with a precision that should be something like twice as good what we have here in this plot.
Is it the same K squared or Q squared? Or
probably the same Q squared bin, yeah. Okay. So very, very briefly, just some introduction to remind you how new physics could in principle enter rare B meson decays. So we're talking about flavor change due to current decays of a B quark to a strange quark, and then 2 leptons. At the energy scale where this happens, you can describe that by a four-fermion contact interaction, a B quark, a strange quark, and let's say a muon and an antimuon. And in the standard model, such a process happens only at the loop level, to the exchange of a virtual top and W boson. And this is one example diagram how something like that could happen. It's called penguin diagram, where you have a photon which goes into plus or minus, which is attached to this W top loop. And then one can estimate, very easy estimate how big the effective coupling constant in the standard model should be. You get a loop suppression factor, you get a suppression factor by Secant matrix elements, and this would parameterize then the effective coupling of this decay in the standard model. On top of that, you can have additional new physics contributions. You can parameterize in terms of a four-fermion contact interaction, and then the new physics contribution would scale like some new physics couplings divided by a new physics scale squared. And then the basic idea is the following: you measure these things as precisely as possible, you predict the standard model contribution as precisely as possible, you compare those two things. If you find a agreement between those two things, you can put bounds on what the possible new physics contribution can be. If you find a discrepancy between those two things, you could attribute that to a new physics effect that is showing up. And if you just put in the the numbers, if you assume there's an order 1 discrepancy between the standard model prediction and the measurement, and if you set the physics coupling to 1, then the scale that you get out of that, so the physics scale is around 10 TeV or so. So an order 1 discrepancy in these rare B2S conditions could be due to some new physics which lives at a scale of around 10 TeV, which is actually very interesting because it's not it is a high scale. It's higher than the scales that we currently probe directly at Correctness, but it's also not fantastically high that it's completely out of reach of maybe future machines. So that would be very, very interesting if these rare B decays could establish that such a new physics scale exists, and then one could actually search for these things directly, maybe in the future.
So there, can you remind me? I mean, this process is related to B to S gamma, right?
Yep. Yes.
And so there is a good agreement with experiments.
There is good agreement.
And
Yes.
theories.
Yes.
And so that probably allows you to reduce the uncertainty of the standard model part here, right?
To some extent, yes. So some of the form factors that one needs to describe these semi-electronic transitions, some of them also enter the B2S gamma transition, and those, and the agreement between those things means any constraint under certain assumptions that if this could be in BS gamma or not. But yeah, there's some information that you can get out of that. Yeah.
Is the level of precision in B to S gamma, is it much higher than this? I mean, it's a less rare decay, right? So
Yes.
there's more precision there.
Yes, so there's more precision in B to S gamma. The branching ratio is something like 3 orders of magnitude higher than those.
Yeah.
And the measurements are at the level of around 5%, if I remember correctly. And then the standard model prediction is, it's level 5 to 10% or so precision. So, so you get strong constraints on certain types of physics that would enter in B2S gamma, but we don't see anything there. I actually will come back to that to some extent later in the talk.
So that lambda NP estimate, of course, assumes CNP of order 1.
Exactly, yes.
So if it's a weakly coupled,
then the
could
scale
be
comes
lower.
down. Yes. So that's then maybe even more interesting, because then it could be already in reach of the LHC now. And I make all these statements, I will actually make much more precise during the talk. Okay. So the LHC is a B factory, so since start of the LHC, the LHCb experiment has collected a lot of data. This is the integrated luminosity that has been recorded by LHCb over the years. They get much less integrated luminosity than Atlas and CMS, for example, because they try to run the experiment in a much cleaner environment, so that they try not to get into the regime where they have 30 or 40 pileup events or something like that. They run the typical environment with typical pileup of around 2 or so. So they are doing it in a much more cleaner environment, and they record each year around 2 inverse femtobar or so. That corresponds roughly to 10 to 12 B quarks that have been produced in the LHCb detector so far. That's 3 orders of magnitude more than what the B factory had. B factories had. So LHCb is actually sensitive to a range of rare B decays that have not been seen at the B factories, all B factories. So if the signature is clean enough, LHCb has a very unique sensitivity to many of these rare B decays, and with the start of LHCb experiment, we got experimental information in many cases for the first time on these rare B decays. There are many decays that one can look at. So we've mentioned already these radiative decays, B2S gamma coming in various variations. We can have the inclusive one, just B to anything that contains a strange quark and gamma. The exclusive one, a B to a K star in the gamma, or you can have a B sub S to a phi in the gamma. There are purely leptonic ones, a B sub S to L plus, L minus. There are semi-leptonic ones, again the inclusive version, B going to anything that contains the strange L plus, L minus, or exclusive versions, B to K LL, B to K star LL, B sub S to phi LL, even baryonic decays are measured at LACb, lambda b to lambda, and then plus A minus. In this talk, I will mainly focus on the semi-leptonic ones, mentioning briefly also the radiative and the leptonic ones, the pure leptonic ones. The semi-leptonic ones are the ones where these discrepancies are showing up. Let's start with one example. Just a reminder what these mesons are made of. Here's a B sub S meson, instead of an anti-P and a strange going to a phi, the S is bar, and a V plus, V minus. And one measurement that LHCb does is the measurement of the differential branching ratio of this decay mode as a function of Q squared, where Q squared is the invariant mass of the two leptons squared, in this case the two muons squared. And what is shown in this plot here, in gray, these gray boxes are the standard model predictions, and then there are measurements by LHCb in black, and this blue ones, these are ancient measurements by CDF. It's actually also had some evidence for this decay mode, but LHCb has now pretty precise measurements at the level of 10-20% or so, and one can see a pretty significant discrepancy in this Q-square region between the standard model prediction and the LHCb measurement. So it's actually at face value that's a 3 sigma discrepancy. The measurement is 3 sigma low compared to the standard model prediction here. Now you might be concerned to some extent about the error bars on the standard model predictions. In order to get these predictions, you need to know the P sub S to phi form factors, for example. Those are to some extent available from lattice computations, but lattice computations turn out to work mostly at very high Q squared. At low Q squared, what people are using are so-called light form sum rule calculations. There's some way to model QCD effects, and it's not exactly clear how reliable these error estimates on the standard model prediction actually are. So it might well be that these uncertainties are underestimated, and we actually should inflate those, and then the discrepancy would maybe not be 3 sigma, but maybe 2 sigma, 1 sigma, depending on how conservative you would be with assigning an actual uncertainty to the standard model prediction. But it looks like that there's, at least at face value, there's this discrepancy between the measurement and this standard model prediction that is typically quoted for this differential branching ratio. We can look at a similar decay. Now B to K, B plus V minus. The only thing we do is now we change the spectator quark here from a strange quark to an up quark, and then we have the B to K, B plus V minus. If there's some funny going on in the B sub S to phi B plus V minus, the same thing should also show up here, because the only thing that you do is change the spectator quark, and the physics shouldn't really, the underlying short distance physics shouldn't really care about the spectator quark. And indeed you see something similar. What is shown here is now, again, LHCb measurement of the differential branching ratio as a function of Q squared. Now this broad band here is again a standard model prediction. Here LCSR, these are light and sum rule predictions that go into the form factors for the peak to K transition. And here indeed the uncertainty that is shown here is pretty sizable. Up here there are also lattice predictions for form factors, which are claimed to have a much better control of the uncertainties and lead to a much narrower band up here. But again, the measurements, they seem to be, at least in this low Q squared region, seem to be systematically below the standard model prediction. Here, at face value, the significance is not as big as before, because here the standard model prediction that has been put into this plot has a much larger uncertainty. So the people who did this measurement were much more conservative with unsigning and uncertainties with the standard model prediction that they show in this plot.
Why is there a missing segment in the middle?
Very good. So you also saw that in the plot before. So what is happening here in this Q square region, this intermediate Q square region, you have large backgrounds from B to K shape psi, and then the shape psi decaying into B plus or minus. So that is a large background. That's why you don't have measurement in this region here where the shape psi sits, and also in this region where the psi to S sits, another harmonic resonance. And also it's very, very difficult to make standard model predictions for these things. So typically, this intermediate Q-square region is blinded out when you do the analysis, both on the mental side and also there exists no reliable standard model predictions in this Q-square region.
How are you supposed to think about these theoretical errors? I mean, when we see experimental errors, I presume those lines are 1 sigma lines,
Yeah.
the experimental lines, and I know what that means.
Yes.
So what do these mean?
Good. I don't know precisely what went into this
So
band
because
here,
you
but
interpret it as 1 sigma, there's no problem, right? There's just some systematic effect.
yes.
You tell me
Yes.
they're all correlated, then there's no problem.
Yes.
So that's why I'm asking.
So
right?
what happens here, I don't remember exactly what went into this particular band here, but typically one would take these form factors, let's say from these Lightcon summary calculations, which depend on some model parameters that go into these predictions, and then you vary these parameters in a certain range, which appear reasonable, and then you look what the spread of the predictions is that result from this variation.
Yeah, but don't you, in the end, have to make some sort of a statement that you should think of that as what, 2 sigma?
Yes.
Something like that. You have to say
Yes.
something like
Yes,
that.
so-
So I'm just asking, how do you personally?
Good. When I look at this and do some combined fit of all this incremental data, the way we do it is we assume that these are, we don't use this prediction which is shown in this. We have our own predictions for the various observers, which again depend on certain Lightcon summary calculations and lattice calculations, which are given with a central value and an uncertainty. And we just assume that this uncertainty is a 1 sigma Gaussian, which we put into our fit.
Okay.
That one can discuss how
So,
reasonable
I mean,
that
like
is.
in this case here, would your method sort of tell you that here in that regime that there is a discrepancy unless you push the parameters in your model by 2 sigma or something like that? Is there some statement like that?
Yes. So actually, our prediction here has actually a small uncertainty in this region. So essentially, what we're doing, we take this lattice computation up here and we sort of extrapolate it here. So this band that we are using is actually smaller. But we interpret then this band as a 1 sigma band, and then this measurement is roughly a 2 sigma discrepant with the standard model prediction, the way we do it.
Okay.
Good. Another decay, the B2K star, in plus or minus decay. Now again, we have replaced the up quark with a down quark spectator. We have the B meson going to the K star, which is an excited version of the kaon, which then decays into a kaon and a pion. So we have a 4-body final state, E going to K pi U plus or minus. And again, you can do the same thing. You can look at the differential branching ratio as a function of Q squared. Again, some standard model predictions here in this is gray boxes and measurements by LACP and actually also CMS, which are again systematically low compared to the standard model prediction. Here the significance is maybe not super high, 1.5 sigma maybe or something like that, but still it's consistent with the previous plots that I've showed, that all the measurements seem to be consistently low with respect to the standard model prediction in this low Q-square region.
So Atlas and CMS can't do this? Can't do any of these measurements?
Yeah, so CMS has some results. Also Atlas has some results. For them it's more difficult because they are in a much more busier environment. But in principle they can do it, and it's mainly a question of how much trigger bandwidth they are dedicating to this stuff. So if they had the will to really focus on that and really trigger on Bs, they could do probably a much better job than what they're doing now. And as far as I know, CMS has done in the last run they had implemented a special trigger which was going after Bs. So CMS, as far as I know, has now a sample of Bs which they are analyzing. So the claim is that CMS, at least for for the moment, should get results which are at least competitive with what LHCb has here in this plot. Oh, good. That's a bit dark, but so what I said before, the B2K star mu plus or minus, we have actually a four-body decay of B2K pi mu mu, and this is how an event display of such an event. So here's the primary vertex where the B meson is produced, and when it travels a bit, and then decays into, oh, thank you, very good. Then it decays into two muons, and the pion and the kaon. So the pion is this orange guy here, and the kaon, and the two muons, and they all come from this secondary vertex where the B meson is decaying. Because you have four particles in the final state, there's actually a lot more information in this decay than just the differential branching ratio. You can look at differential distributions among various angles between these final state particles, and then you can actually get much more information from these angular distributions with respect to only looking at the differential branching ratio. Thanks. And so that is what LHCb does is it basically takes the full generic angular distribution that such a decay can have, just based on the fact that we have four particles in the final state with an intermediate one shell K star, and you know the spins of the various particles involved here. Just write down the most generic form this angular distribution can have in terms of three angles. There are three angles: theta L, theta K star, and phi. So theta L is the angle between the muon and the K pi system. The theta K star is the angle between the kaon and the muon system, and then phi is the angle between the two decay planes that are spanned by the plus or minus system and the K pi system. And then you write this generic form of the angular distribution, and each of these coefficients in front of the sines and cosines of these angles, each of these coefficients is an observable that in principle can be measured. And what LHCb does is it just takes this generic form, and then they fit their angular distribution to this form and extract all of these individual coefficients. Some of these coefficients have some intuitive interpretation. The coefficient here, this AFB, is a so-called forward-backward asymmetry. That is the asymmetry that you get when you count how many of these mu minuses go in the, I think, in the same direction as the K pi system, or in the opposite direction as the K pi system, and this is described by this coefficient AFB as a forward-backward asymmetry. The other coefficients, again, you can in principle think of them sort of generalized symmetries, but then you not only take into account the angle of the muon, but you have to, in many cases, have combined the symmetries with respect to several of these angles. And if you slice your parameter space in a particular way and subtract certain parameter space regions from each other, you can always extract also these other coefficients in that way in principle. Anyway, so one of the measurements is now shown here. This is forward-backward asymmetry. And this forward-backward asymmetry, again, is a function of Q squared, seems to agree reasonably well with standard model predictions. Standard model predictions are here now these purple boxes. And again, measurements from LACP and also CMS. CMS is pretty large, and certainly so LACP has the most precise measurements. And, well, they seem to agree indeed reasonably well with what expected from standard model. There's another observable which doesn't agree very well, where the agreement is not very, very good. That's the observable called T5 prime. And that's a particular combination of some of these angular coefficients that I showed before. That's this angular coefficient S5 divided by the square root of FL times 1 minus FL. That's a funny way to define such an observable. The thing is why that this P5 prime introduces is because one can show that in this particular combination of angular observable form factors drop out in the heavy quark limit. So in the limit where the B quark mass is infinitely large, one can show that this particular combination of angular coefficients is actually free of form factors. So in some sense, this P5 prime has been advertised as a theoretically clean observable. Yep.
I think, is it the point at 5 that gives you the 2.5 sigma? The discrepancy? Those
Yes,
points?
yes. I think in this bin here, if you take the LHCb measurement, this is around 2.5 sigma from the standard model prediction.
But there is a point downstairs for another experiment, so
Yeah.
if you combine them, would you get something less significant?
So there's the one down here. There's also one up here. So if you combine those three, but there's some not very good consistency between those measurements. But if you do a naive combination of those three measurements, you end up very close to the actual central value from LHCb, and you stay around 2.5 sigma discrepancy. There's also some discrepancy in this thing here. Again, dominated the measurement here is by the LHCb result, which is also around 2 sigma away from the standard model prediction here. So if you do this exercise, simply averaging all these measurements from LHCb, Atlas CMS, also from Bell, you find that there is, in particular in these bins, each I think a 2.5 sigma discrepancy. Again, you see the same thing as before. Here you have these regions where there are no measurements, where the shape psi sits, and also the psi to S resonance sits. Okay. So question is, could these things be signs of new physics? So we have the discrepancies both in the differential decay rates, also in this P5 prime angular observable. Other angular observables like for vector symmetry do agree with standard model predictions. So could something like that be a sign of new physics? And in order to answer that, one has to try to add possible new physics contributions to these decays, and check that whenever you try to fix one of these discrepancies, you don't introduce discrepancies in other observables that do agree very well with standard model predictions. So trying to find a new physics explanation for this particular set of discrepancies that is observed is by itself a non-trivial thing. So the way you would do it, you would start again with an effective description of these decays, an effective Hamiltonian, which describes the B2S LL transition, and then you just add all possible dimension 6 operators which could contribute to such a decay. There are dipole operators, B2S gamma operators, which can contribute, and this photon couples to mu plus mu minus. Or you can write down directly four-fermion contact interaction between B quark, strange quark, and mu plus mu minus. And depending on which chirality structure you put into this four-fermion contact interaction, these coefficients, these new physics coefficients, they get different names. If you have a left-handed B going to a left-handed strange in a vector current for muons, this thing is called C9. If you have right-handed current for the quarks, it's called a C9 prime. If you have axial vector currents for the muons, you have C10 and C10 prime. And then you could also have scalar currents for the quarks and the leptons. And here for the dipole operators, this dipole interaction between the B and the strange and the photon, these coefficients are called C7 and C7 prime. Yep.
You can also have derivative operators as well.
Yes, so one can show that those are those would be not linear independent of these guys that are written here. That's actually a complete set of a basis of dimension 6 operators that contribute to this decay mode. If you count up to dimension 6 and take into account the full H symmetry of the standard model, or SU2 cross U1 invariance. So these are actually, this has been shown that this is a complete set of these operators. I think I have a comment down here. So one could also think about tensor operators where you have a sigma mu in between the quarks and the leptons. Those turn out to be secretly dimension 8, so you will need some additional Higgses to write them in a SU2 invariant way. Good. So we parameterize the new physics just in terms of these operators and try to understand if there's any of these operators or any combination of operators which would allow to explain the discrepancies without leading to more discrepancies in other observables that do show agreement. And this indeed is a non-trivial task because the various decay modes that we are looking at, they depend on different combinations of the various diffuse coefficients. In particular, the B2S gamma transitions, they depend on this dipole coefficient C7 and C7 prime. The purely electronic decay, the beta S to plus or minus, this one depends very sensitively to this scalar coefficient CS and DS prime, and also to some extent to C10 and C10 prime. And the semi-electronic ones, they are sensitive in principle to all of these coefficients at the same time. And we said before, the B2S gamma transition actually agrees very well. So there we have good agreement between standard model predictions and experimental results. The same is true for this purely electronic decay, the beta S to plus or minus. Also there, one has reasonably good agreement between measurement and standard model expectations, while in the semi-electronic ones we have discrepancies. So one needs to identify now coefficients which allow to explain these discrepancies without introducing more discrepancies somewhere else. And the way we do it is through global fits. So we take into account all the information that we have, all the experimental information in the various measurements, and we put them together in a global fit, switching on the various physics coefficients, trying to identify some which can alleviate the tensions or which can explain the data best. And so we started doing that several years ago in 2011, already before these discrepancies showed up. And by now there are actually many groups which do these global fits. There's several groups which use different subsets of experimental data. We have different ways to parameterize our hadronic uncertainties, which go into the standard model prediction. There are different statistical approaches in combining the information. So there's actually a lot of cross-check between these various groups, doing various complementary approaches. But overall, it seems that there is some sort of agreement that there is indeed some indication that there is a possible physics explanation for all these things. The main disagreement between those groups is about the actual significance of the effect. And so what we find is the following. So this is now results from fits to single Wilson coefficients. We switch on, for example, to the physics coefficient C9, and then we ask how much better does this model do compared to the standard model. And what we find is we do a simple chi-square analysis, and we find that the square root of the delta chi-squared that we get when we allow for new physics in this C9 coefficient is around 5. So we get a pretty big improvement of the chi-squared by allowing for new physics in C9. It also works pretty well if you say that C9 is equal to minus C10. That corresponds to a left-handed current for the muons. That works almost as good. The other new physics coefficients don't do such a good job. There's only very little improvement compared to the standard model. Now this number here, this square root of delta chi-squared of 5.2. Of course, that one in that number, what enters there are our theory uncertainties and our assumptions that we make on our theory uncertainties. And one can argue that we are rather aggressive with these uncertainties. So one could say that probably we are underestimating to some extent the standard model uncertainties, form factor uncertainties that go into that, other hadronic effects that need to be taken into account. So if you inflate these uncertainties, then of course this number here will go down. In general, should keep in mind that the statement that I'm doing is indeed that I'm proving a delta chi-squared when I do that. I don't know precisely how I should attach a significance to that number. There are something like order 100 measurements which go into this global fit, so these various observables that I've showed, differential rates, the angular distributions all in several q-square bins, so there are order 100 experimental results which enter. A handful of them, or the 10, show these 2 to 3 sigma discrepancies. So one should take into account something like a look elsewhere effect when one tries to quantify what the actual significance of that thing is. But at least at face value, it seems that with new physics one does much better than the standard model alone. Okay.
Are the main differences between these different groups just how they treat the theory uncertainties, or is there something more?
That is the main difference, I would say. Some people only take into account LACP data because they are the most precise and completely disregard other results. It doesn't change much because LHCb is indeed the most precise measurements. But yeah, the treatment of the hadronic uncertainties is the main difference between the groups. And then you typically see delta chi-squareds, squares of delta chi-squareds between, let's say, 3 and 6 or so floating around.
Could you explain about the reason guys? The last column, 5.2 sigma, does not mean it's improved by?
Yes, that means that the chi-squared improved by 25 by introducing a non-standard value for this coefficient C9. It's quite a big improvement, but yeah, here's are my cautionary remarks about how
So
to
it's just the
interpret
delta chi-squared.
It's delta chi-squared, yes.
I was wondering only 2 to 3 sigma. What do you mean by improved by 5 sigma?
Okay,
Okay,
yes,
that's fine.
okay, good, yep. Okay. And here you can see what happens when we do it in a 2D way. So here we have now new physics in this coefficient C9, here the physics in this coefficient C10, and the data is now split up into the various experiments that we're looking at, Atlas, CMS, LHCb separately, or if you only take into account the differential branching ratios, only differential branching ratios will end up in this region here. Combine everything gives this red contours. So the best fit point is here, corresponds to a C9 coefficient of around -1 or -1.2. In these units is a particular way of parameterizing that. So in the standard model, the C9 in this unit would be around 4. So it's a minus 25 or 30% the physics effect on top of the standard model. It makes sense. The standard model is 4. You have this destructive interference with new physics, so that brings down all the branching ratio. And it also happens that this value for C9 fixes this P5 prime anomaly in the angular distribution, and at the same time doesn't affect much, for example, the forward-backward asymmetry, which is more or less, or which still remains in agreement with this value of new physics coefficient.
Does the non-zero value of C9 has no Q-squared dependence, right?
Yes.
And we're trying to fit that
Yes.
deficit at a certain Q-squared.
Good. Yes.
So how does that work?
So the fact is that the way this coefficient enters in the amplitude of these decays, so this coefficient comes with a non-trivial Q-square dependency because it's multiplied by certain form factors. The new physics amplitude, yes, comes with this form factor. Also, standard model amplitude has a very highly non-trivial Q-square dependence because there are contributions from virtual photons which go as 1 over Q-squared, other contributions which are flat in Q-squared. So the standard model itself has a non-trivial Q-square contribution. You put on top this C9, which by itself has no Q-square dependence, but multiplied by a non-trivial form factor, and that's the thing
That's the job.
that does the job. Yes.
Okay.
Okay. So the question is, so is this a physics effect, or could that be some underestimated hadronic physics that we are missing here? And to zeroth order approximation, these amplitudes that enter into this B2S and L decays, they can be factorized into these Wilson coefficients, so this coefficient of the effective Hamiltonian of the dimension 6 operators, times some form factors which describe the hadronic physics that goes on in this transition from the B meson into some other meson. but that's only true up to the fact that this factorization holds, and it doesn't hold. There are non-factorizable terms, non-local terms, which break this simple relationship. So there are also effects like that, where you have a four-quark operator here, for example, a P to S and two charm quarks. Then you can these charms then can run the loop, spit out a photon, and again go to L plus, L minus. These things are not captured by form factors and lead to some additional hadronic contributions which are not very well understood and have to be modeled to some extent. And then the question is, or a big question is, how big can these effects be? And there are estimates of how big they might be or should be. And these estimates seem to indicate that they are actually much smaller than what would be needed to explain the discrepancies, but there's no real proof that says that they are indeed so small. They could be much larger than what people think, and then they might lead to significant contributions and might be to some extent responsible for the discrepancies. And the reason why that is the case is because these non-local effects, these non-factorizable hadronic effects, have exactly the same chirality structure as this four-fermion contact interaction with a vector current for the muons and this left-handed transition from the B quark to the strange quark. So the four-fermion contact interaction here, this goes through the weak interactions through W exchange. So we have a left-handed B going to a left-handed strange in this diagram. And here we have a photon which couples vectorially to the leptons. So the chirality structure of that thing here is exactly the same as the chirality structure of new physics that would enter through such a C9 coefficient. So there's no, it's very difficult to distinguish those two things at face value. So it might be that what we're observing here are actually very large non-factorizable effects that are unexpectedly large, but they might show up in this rare B decays. So how can we distinguish them? There are certain properties that these two options have that we can try to exploit and try to separate those two things. So new physics in form of this coefficient C9 is described by this local four-fermion contact interaction. Hadronic contributions are non-local, non-perturbative effects. On the one hand, that means that if it's new physics, in terms of a C9, it would be universal for all processes. So it should show up in the same way in B to K, B to K star, B sub S to phi, and so on. If it's some hadronic effect, it could very well be process dependent. There's in principle no reason why in the B to K star transition this hadronic effect should have the same size as in the B to K transition. So if you see pronounced different effect in various processes, then this would be an indication for hadronic contribution and could not be explained by a new physics effect. Similarly, a new physics effect would be the same for all finite state helicities. For example, in B to K star, the K star is a vector. For the various helicity states of the K star, the effect should be the same if it's new physics, but could be helicity dependent if it's a hadronic effect. If it's a hadronic effect, it could be Q square dependent. So I showed before this diagram with a charm loop. So it's reasonable, or it would be a reasonable assumption that this charm loop actually becomes more and more important the closer you get to charmonium resonances. While if it's a new physics effect in C9, then by definition this C9 would be a Q squared independent quantity, and therefore ends up with a particular well-defined Q square dependence on these plots of the branch ratios. The other way around, so the physics could be CP violating while hadronic contributions are CP conserving. So if you find these discrepancies show up differently for B's and B bars, this would be a clear indication that it's a physics effect and could not be explained by something hadronic. And, most importantly, if it's a physics effect, it could violate lepton flavor universality. While hadronic contributions, they have to be lepton flavor universal. So there's no way that QCD effect, a non-perturbative QCD effect, could introduce some lepton flavor non-universality. It's just a coupling of the photon to the leptons, which we know is universal. So hadronic contributions have to be lepton flavor universal.
if you wanted to really try to, I mean, one of the things that's a little bit bothersome about this is that all of these discrepancies are, you know, of order the standard. The new physics contribution looks like, if I've understood, that it's of order the standard model contribution.
Yes, something like
which is a
25%.
very,
Yeah.
which is a big cosmic coincidence, right? Because
Yes.
they depend on completely
Yes.
different parameters.
Yes.
On the other hand, it's exactly what you would expect if there was a problem in either the measurement or the theory. You would expect a deviation
Okay.
of order of
Yes.
the
Yes.
signal, right?
Yes.
So you know, so it's a natural question to ask if you wanted to really try hard to attribute it, this measured discrepancy. So let's take the measured discrepancy as truth, and then, you know, attribute it to some sort of hadronic uncertainties like this. Is it really a complete stretch? What's your sense of that?
So I don't know. I'm not an expert in these calculations that people are doing to estimate these hadronic effects. The claim is that the only estimates that exist, they find hadronic effects that are something like a factor of 5 smaller compared to what you would need to explain the data. I think so. They are so formally they are. Well, there's an expansion in the heavy torque limit. So these are effects which are suppressed by 1/mb. So some sort of lambda QCD over mb effects, which could come with some, and then they are calculated in using again some modeling of QCD using some light cone sum rule input, and if for some reason these estimates are off and these coefficients with which these lambda over mb corrections come are a factor of 5 larger than what comes out from this modeling, then you could explain it. I don't think it's a complete stretch. I think that is a possibility.
But there isn't a more clean statement like I would need, you know, 1/mb corrections to be 5 times larger than I expect. I mean, is it really just somebody did some model estimate and they did an honest job of saying what they think the uncertainties are, and then you multiply their uncertainties by 5?
Yeah.
That's very hard to judge whether that's different from saying, you know, we have a systematic expansion and we expect the errors to be small. There's at least a parameter there. Is it, you know, if it's like that? Or?
It's not really a systematic expansion.
Okay.
Yeah, that's the problem. So the thing that might be the point that decides that is indeed this lepton flavor universality. So that will be the point that I will make.
There you'd have to rely on something like the fact that, you know, I mean, muons are heavier, so you've got a slightly different kinematic regime
Yes,
or
yes,
something like
yes,
that, right?
yes.
You'd have to push that.
That's true. That's true. That's true. But so we did check several of these points. One thing that we looked at is the Q-square dependence of the tensions. So what one can do is one takes into account data only in certain Q-square regimes. So if you split up the data such that you only take measurements between 0 and 2 GB, between 2 and 4, between 4 and 6, between 6 and 8, and so on, and you separately fit what this new physics coefficient C9 should be based on this data, you get those results here. So, yeah.
Larger Q, larger than this,
Yes.
you would expect the hadronic corrections to be less significant because you're more into the perturbative regime. Because you have data in the larger ultra large Q squared.
So the data goes up until around 20 GeV squared, which is just a kinematical endpoint, so you don't have higher Q squared available just from the B meson decay. So we could do in principle we could extend the plot up there. So there's the data up there is not as good, but you would find some box somewhere here with a pretty sizable uncertainty, in principle compatible with a constant C9 of around -1.2.
Just like to think related to the previous point, how important those hadronic corrections. At larger Q, you would expect them to be less important.
Well-
So that could be like your probe or
I
something.
mean, the Q is
If you
still
have-
pretty small, so the question is how reliable your productive expansion would be up there. And indeed, so what one sees at high Q squared are broad tramonium resonances. So I was mentioning before that there are these narrow tramonium resonances, the shape psi and the psi to S. At higher Q squared, there are broader tramonium resonances, which actually are seen in the data as some wiggles in the branching ratio. And those are also very hard to predict theoretically. So it's very difficult to make very precise calculations also in high Q squared. Anyway, so the point of this plot is to show that there's no pronounced Q square dependence in these best fit values for this physics coefficient. So it is compatible with a new physics effect, but it's also compatible with an hadronic effect, which simply doesn't show a pronounced Q square dependence. We also did the same with helicities. We looked at different helicities during fits. Don't want to go into details because I'm running out of time, but again, we didn't find any helicity dependence, no pronounced helicity dependence, so it could be new physics, but it also could be a hadronic effect. And now we're back to the lepton flavor universality test from the beginning. So I had argued that if it's a hadronic effect, it shouldn't be lepton flavor non-universal. However, if it is new physics, it could be lepton flavor non-universal. And this here seems to be a pretty nice indication that indeed there is some lepton flavor non-universality in these decay modes. If you now look at this RK, which is now defined precisely as the branch ratio of B to K, B plus or minus of the branch ratio of B to K, E plus E minus in a Q squared bin from 1 to 6. You would expect it, no matter if this is completely standard model or if there's some lepton universal new physics contribution inside, this thing should stay 1. The only way this could be not 1 is if there's some lepton flavor non-universal new physics contribution in that. If there are underestimated hadronic effects in B to K, B plus or minus, then the same should happen in B to K, E plus or minus, so those things should all cancel out in this ratio, and you should get 1. However, the measurement is around 0.75 with 10% uncertainty. So there we have a 2.5 sigma indication that indeed there is some lepton flavor non-universal thing going on in these decays, which could not be described as a hadronic effect.
So does the E plus E minus agree with the standard model prediction then? Is that the way it's working?
Within its uncertainties, but there the measurements of the B to K, E plus E minus branch ratio actually have much larger uncertainties than the muons. So in principle, this branch ratio could be standard model, like it could deviate from the standard model. There are large uncertainties at the moment.
It looks like there's around 100 or a few hundred events in there, probably, right? And I'm guessing that if you looked at the distributions inside that bin, say as a function of Q squared, there's nothing, people have looked, there's nothing interesting there. They're just kind of,
Yes.
right.
Yeah.
Earlier there was a rumor saying about this number, right? But then it was denied or something. Do you
So
know anything
Good.
inside?
Good. So the update from LHCb that I heard of, so the rumor says that the new number, I think it's 0.85 now. So if you include the run 2 data, I think the number goes up to 0.85 with an uncertainty of around 0.06, I believe. So it's still a 2.5 sigma from the standard model, but the essential value moved up a bit closer to the standard model. So that's the rumor that I heard. I guess we will know in 3 weeks at Moriot as opposed to show the official numbers there. So that's RK. There's also RK star. Same definition, the branch ratio of B to K star mu plus minus over B to K star E plus E minus measured in 2 Q squared bins. They're around 0.65, 0.7 or so with 0.15 or 0.11 uncertainty here. Again, around 2.5 sigma in each of these bins, away from the standard model prediction of 1.
And less than 1 means too many muons or too few muons, or just for
That means too few muons.
too few muons.
So that is compatible with the individual measurements of the branch ratios for muons, which were all below the standard model predictions. And indeed, if you now, one thing I want to mention is how robust are the standard predictions of one versus RK and RK star. So you might wonder what's the precision on that. And so the thing is that the phase space effects are actually tiny. The fact that the muon mass and electron mass are not exactly the same are very small effects. Only for very small q-squared this becomes an issue. Apart from that, this is sub% or per mil effect. Due to the fact, or given that there are these phase space effects, this cancellation of hadronic effects is not exact. So there will be order lambda QCD over MB and other alpha S corrections to RK and RK star, but only up to the amount that these things go as mu squared over q squared. So even though these might be large uncertainties, and I might argue that this is maybe not under good control, they might be maybe much larger than one would naively expect. These things get multiplied by mu squared over q squared, so you don't really care for the standard prediction of RK. The thing that one should care are QED corrections, so emission of photons, which is very different for muons and for electrons. But the claim there is that this is very well modeled by Monte Carlo, that is used by LHCb. So they take into account by modeling this photon emission by Monte Carlo, and this seems to match very well what is predicted by analytic calculations. And then the people looked into that carefully, and the claim is that indeed RK and RK star in these higher q-square bins should be 1 with something like a 1% uncertainty, and in this lowest q-square bin of RK star, the prediction is here around 0.91, mainly because of phase space effect, and then with a slightly larger uncertainty. But still, these uncertainties here are much smaller than the discrepancies that are observed.
So you don't, well, why don't you finish your talk?
Okay.
Finish it, I've asked
Yes.
the question.
So let me switch to this plot here, which shows again now this plane of C9 and C10. So now muon-specific modifications of these four-fermion contact interactions, and what is overlaid is the result from this fit of only the muon data that I showed, the branch ratio of the muons and the angular observables for the muons in red, and then in blue are the results from this lepton flavor universality ratios, and they overlap really nicely. So it's fully compatible. These lepton flavor universality observers RK and RK star, those give values for C9 and D10 which are fully compatible with the other anomalies. And the best description of all the anomalies is given by new physics that is specific to the muons. Some physics that affects this coefficient C9, which is muon-specific, as before, only by effect around minus 25% compared to the standard model, and that electrons are more or less standard model-like. This gives a very nice and consistent picture of all these various anomalies. And so now, if you take this serious, you can ask what is the scale that is actually associated to these effects. So again, if you take this four-fermion contact interaction, which corresponds to this coefficient C9, then you put in some numbers for the Newton coupling. If you just some generic tree-level effects and order 1 coupling, you find that this is a Newton scale of around 35 TeV. If you put in some suppression factors, some CKM factors, or some loop factors and CKM factors, you get to lower scales, somewhere between a few hundred GeV and several TeV. And if you push it all the way up to something like a unitarity bound, if you put here a 4 pi for the coupling, you end up with something like around 100 TeV. These are the possible ranges of physics scales that would be compatible with an physics explanation of the anomalies. My favorite model is the following. It's a C prime gauge boson, which is based on gauging the difference of muon number and tau number. This is something you can do with the standard model field content, where mu and tau is anomaly free. And then you get a C prime which couples vectorially to muons as you would like. And then you have to have some way to couple the C prime also to the quarks in a flavor violating way. You can do that by mixing it with, by mixing the standard model quarks with some heavy vector-like fermions, which are charged under muons and tau and coupled to the Z prime. And then you can engineer such a coupling for the Z prime, which then gives indeed a contribution to C9, which can be of the right size if you choose these couplings appropriately. What I should mention is that this first paper that we wrote about that came out before the measurements of RK and RK star. So actually we mainly try to explain the P5 prime anomaly at that time. And we actually have a prediction in this paper that there should be lepton flavor universality violation. It's a level of 20-25%. And this is exactly what fits with the measurements of LHCb that came out afterwards.
But you have too many offers for a Nobel Prize.
Yes, unfortunately.
You have to kill somebody.
Yep. This is the parameter space of this C prime. Here's the mass versus the gauge coupling, this mu and tau gauge coupling. There are several constraints that one can look at. If you want to explain the anomalies, the C prime should be heavier than the B meson. Here I put a cutoff at around 10 GeV. Otherwise, this C prime would show up as a resonance in the muon spectrum from these B decays, and something like that is not seen. So you have to be heavier than that. But if it's above 10 GeV or so, it could be much heavier. It could be up to several TeV. The only thing you need is then a gauge coupling, which is of order 1. But apart from that, there's this parameter space where you can explain the anomalies. The strongest constraint in that case come from B sub S mixing, which gets treatable contributions from this C prime as well. And then there are also results from what is called neutrino trident production. It is a dimuon production, the scattering of neutrinos on a heavy nucleus. It's actually turns out to give the strongest constraint in this upper region here. And there are actually also direct searches for dimuon resonances at the LHC, which carve out important parameter space. But in all this white region here, this C prime can in principle explain the anomalies. Okay, just a final word on the future prospects. As I mentioned, we are supposed to hear very soon an update from LHCb, and in principle the LHCb can push down the uncertainties on RK and RK star quite a bit. So if they assume they run until 2040 or so, they could in principle reach uncertainties at the level of 1 or 2% or so, assuming that they can control their systematics. So I think this only takes into account the statistics that they will be accumulating. At the moment we are here. This is the run 1 data that has been analyzed. Soon we will jump to here, and the run 2 data will be analyzed. Then we will be in this sub 10% regime for the uncertainties. Soon also Bell 2 will enter the game. So Bell 2 will start running later this year. They will start collecting data, and with their nominal plan of running in a few years, they should also reach this sub 10% or maybe 5% uncertainty on this RK and RK star lepton universality ratios, and then I should be able to get a much clearer picture if there is something going on in these ratios or not. Okay, let me stop here. As I discussed, there are several observables in rare B decays that show discrepancies with standard model predictions. I've mentioned these branching ratios and also angular observables. Those things could be due to new physics or due to some hadronic effects, which are not very well understood. But if you combine that with these lepton flavor universality ratios, I think then one can make the case that this actually should be a new physics effect. And if these hints for lepton flavor non-universality get confirmed with more statistics, then they indeed point clearly to a new physics effect. And with more data, it should be possible to sort this out. Okay, thanks.
So maybe I missed it, did you have a favorite mass with this Z prime?
Not really. It could be anywhere between 10 GeV and let's say 10 TeV or so. So broad range of C prime masses that can in principle work. You just have to adjust the coupling appropriately to be able to explain the effect.
Yes, if it's lighter, you would pick up some anomalous Q-squared dependence.
Exactly,
But
exactly.
you don't see
Yes.
the sign of that.
Yes, yes.
Why does the LHC search fall off at, looks like 20 GeV? Am I getting that right?
You mean here?
Yeah.
So what they're doing is they're looking for the decay of the standard model C boson into four muons. So that dies off I think it should die around 90. Yeah. They could do because then you get the Z going into two muons. One of the muon radiates off this C prime, so you have this three-body decay of the Z, but the Z prime then goes into plus or minus. In principle, you could do the Z to fermion with an off-shell C prime, which should extend this to some amount, but I don't think they did that.
Can you not produce the Z prime directly through this port coupling, the mixed port coupling?
Yes, this coupling is actually pretty small in order to avoid the constraints from east of S mixing.
I see.
So you want this coupling to be as small as possible, and then it's just not large enough to lead to an appreciable production rate at the LHC.
The Qs, the intermediate Qs, the
Yep.
couple,
Yes.
they're colored, right?
Yes,
So
yes. But they could be 10 TeV or so. Don't produce them really at the LHC.
So if you had kind of like a click feather collider, high energy leptons, you could. Oh, I guess no, because this is still electrons, so it doesn't matter.
Yeah, so this
Even
particular
muon
thing doesn't
collider.
couple to electrons, yes. Yeah.
Right, right.
Yes, a muon collider would be perfect for that thing. Yes.
Any other questions?
So if the anomaly is persistent in the future measurements,
Yep.
and what else you would know what exactly causes it?
Good. So what you want to do is you want to measure first of all these angular distributions also for electrons, not only for muons, to see or to get more information about the actual chirality structure of the interactions, of the physics interactions that is behind that. If you take the conservative point of view that even though in the muons there are these discrepancies, maybe those things are not very clean, and you only want to stick to the lepton flavor universality measurements that give you a clean indication on the physics. And then you want to, essentially what you want to do is you want to look at lepton flavor universality violation in the angular distributions of B2K star mu versus B2K star EE. And then you should be able to at least identify uniquely what is the chirality structure of the physics interactions which is responsible for that. And then beyond that, from low energy measurements, you cannot do much more. Then you would need to trying to find whichever physics is that mediates these interactions. It could be a Z prime, it could be leptoquarks, that is something that people are discussing quite a bit. But the low energy will not be able to distinguish those things.
Isn't there something else? I mean, like in this model, it looks like the electron one is entirely described by the standard model.
Yeah.
So
Yeah.
if you get a lot more data, you could start looking at the distributions of just the electron one or just
Yes.
the muon ones, like angular
Yes.
distributions,
Yes.
and see whether you've correctly predicted those.
Yes.
Right? If
Yep.
they're both off, of course it could still be that there's new physics in both, but then
Yep.
it starts looking fishier, right?
Yes, good. Yes, this is something one can do.
Yeah.
Yep. The other thing that this particular model does, it predicts very precisely what the taus should do. So because you gauge L mu minus L tau, everything what you do to muons, you get the opposite effect in the taus. The only problem is that those
And the
decays,
kinematics
it's very, very difficult to measure because you don't reconstruct the taus because you also have neutrinos inside there, so these measurements are very, very difficult to do. But yeah, that would be, in principle, that would be the smoking gun prediction of that particular model. That B to K star tau tau should be enhanced by 25% with respect to the standard model.
Have any kind of measurements been made there at all, or is it just?
So that there exists some bounds from the B factories, but they are, I think, 2 or 3 orders of magnitude above the standard model prediction. So it's unlikely that one will reach standard model sensitivity in the near future.
Within this model, how much can we feel this uncovered area in the future?
It's very, very difficult. So for pizza best mixing, the measurements are very, very precise. The main problem here are, again, standard model predictions, which have uncertainties, which come from lattice computations of hadronic matrix elements, which are at the level of 10% or so at the moment. So if you trust that lattice computations will improve these uncertainties by a huge amount, then these constraints here would start moving in this direction. Then you could start to cover it. Coming from the other side, from above, these tridents, neutrino tridents, their measurements will likely not improve by much. So we did recently, this paper which came out last week, we did a study of how well the Dune experiments should be able to measure these neutrino trident cross-section. And we saw that it actually will not improve this high energy range, only in the low energy, in this very low mass regime, could carve out new parameter space.
So we can cancel it.
Yes. The other thing, if I guess there are results from LAC here, which is just measurements of Z to LL, measurements of the lepton universality in Z decays. If you build a FCC-EE and measure those things with much higher precision, then you should start to move into this parameter region up here. So there are in principle things, but this particular model, this particular prime model is actually pretty robust and not very easy to exclude based on the things that we have identified so far.
If there are no more questions, let's thank Wolfgang.